Hello guys, how are you again? In our lesson today, we're going to talk about the molecular polarity and dipole forces. And before starting with this lesson, first we have to know that we have two types of forces in compounds, which are, as you can see here, intermolecular forces, and the other type is intramolecular forces. So we have intermolecular forces and we have intramolecular forces. And the difference between them, when we talk about the intramolecular forces, we mean that we are talking about the covalent and ionic bonds, because they are intramolecular, which means inside the molecule itself. So when we are talking about molecule like water, for example, that means that the intramolecular forces inside the water molecule is a covalent bond. While when we are talking about this type here, the intermolecular forces, that means that we are talking about forces between molecules. So for example, if we have here H2O, this is water. When we are talking about OH and H, now the covalent bond here is intermolecular forces. But what if we have a water molecule here and another water molecule here in the compound? Do we have any type of forces between these two molecules? Now, these forces, what we mean by intermolecular forces. So, in our lesson today, we're going to talk about the intermolecular forces, which are exist between polar molecules and non-polar molecules. But here, as a start, we're going to talk about a type of intermolecular forces which called dipole forces. And as you can see here on this page, the strongest intermolecular forces exist between polar molecules. And the polar molecules act as tiny dipoles because of their uneven charge distribution. So a dipole is created by equal but opposite charges that are separated by a short distance. So when we are talking about, for example, a molecule like HCl, we know that the charge for H is 1 positive and it is 1 negative for chlorine. So the charge is 1 for both of them, but with opposite charges. So here, HCl, hydrochloric acid, we are talking about a bond between hydrogen and chlorine. And here we will have a negative charge with a positive charge at hydrogen atom. So the electrons will be this side. So here we have negative pole here and positive pole here. So this is the dipole because we have two poles. Of course, here we have a total charge, and sometimes we could have a partial charges, like for example, if we are talking about H2O, the H will be partially positive and oxygen will be partially negative because the electrons here are just closer oxygen. So they are not totally removed from hydrogen orbitals, so hydrogen will be partially positive charged. While, for example, when we are talking about molecule like Br2 here, Br with Br, as you can see, they both have the same electronegativity, so the electrons will be distributed exactly in the middle between two atoms, so it will be an even distribution, so we will not have a polar molecule. So the effect of a dipole-dipole forces is reflected by the significant difference between the boiling points of iodine chlorine and bromine. Now the negative region in one polar molecule attracts the positive region in the adjacent molecule. So this is how we will have a dipole-dipole force. So for example, if we have HCl and we have another HCl here, this will be the positive one and this is the negative side, and here we have the positive, here the positive and here is the negative, and this is it. So the attraction will happen between this side with the positive side with the other molecule, and so on here. So this is the attraction that we called dipole-dipole forces. Now, the effect of dipole-dipole forces is reflected, for example, by the significant difference between the boiling point of iodine chloride, ICl, and bromine. Because Br2 here, as you can see, it is a non-polar molecule, while ICl is a polar molecule. So we will have a dipole-dipole forces here in ICl because the molecules are connected with each other stronger than the molecules here in Br2 case. This is why the boiling point for ICl is higher than the boiling point of Br2. So the dipole-dipole force is responsible for the relatively high boiling point for ICl. And as we can see here, this is how the attraction happens between different charges. Notice that each negative charge is attracted to the positive side of other molecule, as we can see. So we have another type of forces inside the compound that are responsible for the physical properties for the compound. Now the polarity of diatomic molecules such as ICl is determined by just one bond. For molecules containing more than two atoms, molecular polarity depends on both the polarity and the orientation of each bond. So a molecule of water, for example, has two hydrogen-oxygen bonds in which the more electronegative oxygen atoms is the negative pole for each bond. Because the molecule is bent also here, notice that we are talking about the geometry for the compound. So because the molecule is bent or angular, the polarities of these two bonds combine to make the molecule highly polar. And ammonia molecule, as explained before, is also highly polar because the dipoles of the three nitrogen-hydrogen bonds are additive, combining to create the net molecular dipole. In some molecules, individual bonds dipoles cancel one another, causing the result molecular polarity to be zero. So it is not a must that if we have a polar molecule or a polar bond that the molecule itself will be polar. For example, when we are talking about H2O, this is O. Now this is the shape of water, as mentioned before, which is bent. Here, this is the direction of the polarity. So the net direction will be this way. While, for example, in a molecule like CO2, this is COO. This is the shape of carbon dioxide, which is linear. And as you can see here, electronegativity for oxygen is higher, so this is the side for it. And the other side, the other bond will be this way. Now here we have a polar bond here between carbon and oxygen, and this bond also is polar. But the polarity is going to an opposite direction, so they will cancel each other. So carbon dioxide is non-polar molecule. So if water was this way, so if water was linear, the polarity will be like this, so they will cancel each other, so water will be non-molecular. But because the shape of water is angular, we will have like a net polarity side, so water is a polar compound. So we could have a polar bond, but the molecule is non-polar, which is determined by the shape of the compound itself in 3D. A polar molecule can induce a dipole in a non-polar molecule by temporarily attracting its electrons. The result is a short-range intermolecular forces that is somewhat weaker than the dipole-dipole forces. The force of induced dipole accounts for the solubility of a nonpolar O2 in water. The positive pole of a water molecule attract the outer electrons, as you can see here on this shape. So here, as you can see, guys, we have water, which is bent. So we have, this is the side of polarity. So the net polarity, we have a net polarity, so the water is a polar compound. Ammonia is the same. This is the triagonal pyramidal, as you can see. So we have a polar compound. Here we are talking about CO2, carbon dioxide. As you can see, opposite direction. So they will cancel each other. So here we have a non-polar compound. And here, if we are talking about Cl4, as you can see. Now, if you look at the shape, it is a tetrahedral, which is carbon tetrachloride. The molecule here, as you can see, is non-polar. So we don't have a dipole forces, because the net of these three bonds will be downward, which will cancel the upward polar bond, as you can see here, polar covalent bond. So remember that here we are talking about the polar covalent bond, and if we have a net consider it as a net force to be easier for you to get it. If we have a net force for the polar covalent bond. And of course, if we don't have a polar covalent bond, so know that we're going to have a polar molecule, as mentioned in previous videos. And as you can see here on this shape, the positive pole of a water molecule here, which is hydrogen, as you can see, causes temporary change in electron distribution of an oxygen molecule. So the oxygen molecule here, we have a non-polar covalent bond, as you know, between two oxygen molecules. So the negative pole induced in the oxygen molecule is then attracted to the positive side of water here. So here, if we have sometimes, just for a moment, for a very short period of time, changing of the distribution of the electrons, we will have like a partial negative charge over this oxygen, which will be attracted to the positive charge of the hydrogen atom here, or the hydrogen side. And this is just for a moment, and after it will be redistributed again, because the electrons will not stay in the same direction. This is our lesson today, which is dipole forces, and our next video will be about hydrogen bond. Thank you, and be safe.